All right, folks, Mr. Bozade here. Let's learn a little bit about LT5b, proportional reasoning. I'm going to work through the problems on the formative, and hopefully this will help you out. So here we go. Let's dive in. All right, number one, a car that is stopped at a stop sign accelerates from rest. Later on, the same car accelerates from a different stop sign with double the acceleration. By what factor is the... Oh, sorry. Okay. I always recommend you just jump straight into part B. I think that's the easiest way to get going. So we know F net equals mass times acceleration, okay? And notice that I space them out like that, so that if I need to put some placeholders in, I can. So here we go. The first thing you want to do is you want to find out what is constant. So it says a car that is stopped at a stop sign accelerates from rest. Later on, the same car accelerates from a different stop sign with double the acceleration. Well, since it's the same car, we know that the mass is constant. So I circle the things that are going to be constant. Then I put a placeholder in front of the things that are changing. So acceleration is changing and net force is changing. We're told that the car then accelerates from a different stop sign with double the acceleration. So maybe I'll change that color. So the factor of change for acceleration is 2. And what we want to do is balance both sides of the equal sign. So if this side changed by a total of 2, right, then this side's going to change by a total of 2 as well. So we can put a 2 right there. So what must have, so for A, what must have been different that made the same car accelerate? Well, the net force must have also changed so that the acceleration changed. And it changed by a factor of 2, as we discovered. So then at the first stop sign, the mass of the car was 1,800 kilograms, and the net force was 6,000 newtons. Calculate the new value for the variable from A. So what we need to do is we're going to double the old net force. And the old net force, as we just read, was 6,000. So we're going to do 2 times 6,000, which gives us 12,000 newtons. And there we go. All right, let's try number 2. A mom. So again, just to recap number 1 a little bit, we wrote our equation. We left space for placeholders. We found the variable that was constant, and then we found how much a variable changed, and then we balanced the equation so both sides were equal. All right, let's do the same thing for number 2. A mom pulls a wagon with a constant force. Her daughter's friend jumps in the wagon, which doubles the mass. She is pulling. Mom keeps pulling, so the same net force is on the wagon. All right, let's go. F net equals MA. I think I saw this time right away that she pulls with the same net force. So I know that this is the thing that's constant, net force. So I'm going to circle that. There we go. So that means these two things are changing. And we know that her daughter's friend jumps in, which doubles the mass. So I know the mass doubles. Now, this is the kind of problem that often confuses people. Often people make a mistake, don't do this, and they say, oh, I doubled mass, I'm going to double acceleration. But that's not what you need to do. And here's why. Because what happened on this side? Nothing. This side stayed the same, right? It didn't change. So we need nothing to happen on that side as well. We need that side to not change. How do we make that side not change? Well, we do it by making the acceleration have a 1/2, so that this 1/2 cancels with the 2, because 2 times 1/2 is 1, which means we're not changing. There we go. So we were told that the mass changed, doubled. So what else changed? We discovered the acceleration changed. So acceleration also changed. And it changed by a factor of 1/2. So let's find the acceleration in here. And we're going to take 1/2 of it. So 1/2 of 0.6 is, so acceleration is 0.3 meters per second squared. There you go. All right, let's do the last one. Again, though, we just followed the same process, right? We started with our equation, which was net force equals MA. We found the thing that was constant, and then we found the thing that changed, and then we found how the other thing changed. All right. Here we go. Let's do our last problem. Dog A and dog B are running around on hardwood floors. They chase one another toward the end of the hallway, and then they skid to a stop. Both dogs accelerate at the same rate when stopping, even though the net force on dog A is 1/3 the net force on dog B. All right, so let's do it. F net space equals MA. There we go. All right, what is constant? Dog A and B, they're running, end of the hallway, skid to a stop. Both dogs accelerate at the same rate. There it is. I found it. They accelerate at the same rate. So that is the constant thing. So these are the things that are changing. And we see here the net force on dog A is 1/3 the net force on B. So we're going to do 1/3 here. And we want to balance both sides. So this side changed by 1/3. So we need this side to also change by 1/3. Since acceleration is constant, the only way we can make the other side change by 1/3 is if the mass changes by 1/3. So what's the other thing that changed? The mass, and changed by 1/3. So we got to find the mass in here, right there. Dog's mass is 50 kilograms, so we're going to do 1/3 of 50. 1/3 of 50 is 16.7, so the new mass is 16.7 kilograms. And there you go. So let's take one last look at all of these to get a little bit of a bigger picture. You definitely get the process by now. I think the most important thing to understand is that when the things that change are on opposite sides of the equal sign, we don't want them to like cancel each other out, right? We want them to change both sides equally, right? So for example, in this problem, number 1, we saw acceleration change the right side by 2, so we need F net to also change the left side by 2. Similarly, in number 3, we saw that mass changed, we saw that net force changed the left side by 1/3, so mass had to change the right side also by 1/3. But in number 2 was a little bit different, right? What we found is that the net force didn't change. So essentially the left side of the equation didn't change, and we want the right side of the equation to not change. So since mass doubled, acceleration had to change by 1/2 in order to keep the right side the same as well. All right, hope that's helpful. See you later.